Can people on Zoom hear me? Yeah, good. Okay, so first and foremost, let's not forget that today we'll have a quiz at 3 p.m. It'll become available on Canvas, and you'll have 24 hours to complete it. You can either turn in a physical copy into the envelope on my door marked for our class quizzes, or you can just submit visually on Canvas pictures of your work. I have a slight preference for actually having a physical copy, but it really doesn't matter. You can do whatever you want. Okay. In my office, 540A 90. An envelope is pinned to the front door. Okay. Right. Oh yeah, and it just covers everything that we did about vectors, dot, cross product, lines, and planes. Everything that we did up through Thursday. Okay. All right. Good. 1.5. Okay. Good. So, having completed our review, let's see, is this off frame? No, good. Having completed our review of everything we need to know about vectors and linear affairs such as lines and planes, we can now start talking about vector valued functions. Specifically, a single variable. Okay, so we wish to study functions of form f hat, we'll put a hat on the function to indicate that its output is a vector, which go from R to Rn. Which is usually written f hat of t is equal to f1 evaluated at t, f2 evaluated at t, all the way up to fn evaluated at t. Okay, so here's our single variable t, right? We have one input slot for one real number, and then we evaluate that on n different functions which have output a single real number, and we organize all the outputs of those n functions into a vector. Okay, so we call these component functions. Right, so that is to say, a vector valued function f hat is defined by n component functions, which just go from the real numbers to the real numbers, right? f1, f2, fn, those are all real valued functions. So we take these n real number outputs and put them in a vector. Okay. Hat called a vector valued function of a single variable. Right. And let me reiterate. The FIs are component functions. I just realized my shoe was on there. Okay, so when we study calculus, yes,
So the output of this function at that is a vector?
that's right. These n components are the components of the vector. Yes. What I mean is where I is between 1 and n for each of these, F1, F2, F3, all the way up to Fn. Yeah, good. Right, so when we study calculus, depending on your instructor, the reality of the situation is that we are concerned with the properties of a function, right? That's what we're studying, whether or not a given class of functions is differentiable or not. That's what we're studying when we study calculus 1, right? So now we're adding a layer of complexity to this because we now will consider things, well, to start, that have vector output. We'll soon get to things that have vector input. And we will, by the end of the course, start to study functions that have both vector input and output. Okay, we'll sprinkle some of that in along the way. But we start with this case of a single variable vector value function because the analogies are very easy to draw for properties of this type of function as those that we studied when we studied single variable functions, just like in calculus 1 and 2. Okay, so here's some important definitions. Okay, so a single variable vector value function, f hat of t, given by f1 of t, f2 of t, up through fn of t. Is continuous let's say, or differentiable, or continuously differentiable, if and only if each fi has the same property. That is to say, for example, continuity of f hat of t is evaluated on each of the components of f hat of t. In order for f hat of t to be continuous, f1 of t, f2 of t, all the way up through fn of t, all have to be continuous. Okay, same for differential. We can find the derivatives. We know how to find derivatives of real functions, right? Those that which just have real number output, real number input. If we can find the derivative of each of these components, then we found the derivative of f hat. Now, what does it mean to be continuously differentiable? You better remember that term.
Take the derivative like a amount of time.
That's slightly stronger. Actually, that's much stronger. But you're on the right track. Any other guesses? Or maybe someone knows. So it's just that when you take the derivative, the function that gives you the derivative is continuous. Okay, so the functions we're used to dealing with, you can usually differentiate as many times as you like, as you would say. However, you can construct certain pathological functions which are differentiable, but only once. Exactly. You take the derivative, you can't take the derivative after that. So it turns out that it's enough, even if you're not differentiable after you take the derivative. Very often we'll study this class of functions where when you take the derivative, you're at least continuous. Okay, because you can construct examples of functions which are differentiable, and when you take the derivative, you get something that is not continuous. Very badly behaved functions. Okay, so very often we'll add this in just to avoid certain pathologies. Okay, and for anyone interested in constructing that function, we should talk outside of class. It's a little bit of work, but if you want to know, you can talk about it. Okay, good. So, right, part 2 here. The derivative of f hat, if it exists, is given by f hat prime of t equal to the limit as h approaches 0 of 1 over h times f hat of t plus h minus f hat of t, which of course is just the same. I already alluded to this. The derivative of f1 of t, comma, the derivative of f2 of t, comma, all the way up to the derivative of fn of t. Right? That is to say, if you write this out explicitly in coordinates, you get f1 of t plus h minus f1 of t divided by h. That's just the formula for the derivative of f1. Right? You get that for each component. This reiterates what I was just saying about f hat of t being differentiable if and only if each of the components is. Okay. Okay, so can anybody tell me an example that we've already worked with extensively of a vector value function of single variable? Yeah.
Like parametric function.
Yeah, a parametric equation of a line, say.
Yeah.
Yeah, good. Right. So very good. So if Q given by Q1, Q2, all the way to Qn is a point of Rn, and V hat in my V1, V2, all the way up to Vn, a vector then P of t equal to Q plus T times P hat In other words, Q1 plus TV1, comma Q2 plus TV2, all the way up to Qn plus TVn. Parameterizes the line in Rn. Right, this is mimics exactly the formula that we wrote down for lines in R2 and R3. Now we just have a point in n-dimensional space and an n-dimensional vector instead of a 2 or 3-dimensional vector, right? Parameterizes a line in Rn. Note that again, each component is the equation of a line in R2, right? That is to say, of a single variable. T. The classic slope-intercept form equation of a line, right? Each component. Okay. Good. So, if we suppose he had a T specifies position of an object. Then the velocity is given as what? Yeah, it'll just be the derivative of the hat, right? Okay, so d of t is equal to e prime, the hat prime of t. Sorry, this is one annoying thing about working with vectors. The notation gets really jammed up here. You get hats and primes. Perhaps even we'll get superscripts and things like that as well. Try to be as clear as possible, but when it's not, please ask. Okay. Right. So let's differentiate this in terms of t. What's the derivative of the first component of p of t, the hat of t? Yeah. So remember, this is our formula for p of t, and the first component is given by p1 plus tv1. Oh, it's just v1, right? It's the coefficient on the variable. The constant, i.e., the first component of the point, goes to 0. Yeah, that's okay. Good. And then differentiating tv1. This is the same old power rule from calculus 1, right? So t goes to 1, so we just get the constant term v1. How about the second component? It's just v2. Which is just equal to our original vector, right? A constant vector. This is just like back in Calc 1. Right? You have a linear equation. The derivative of that is a constant. Something is moving in a linear fashion, its velocity is constant. Yeah. Same thing here. Although now we've slightly altered the notion of what a constant is, a constant vector. Okay. Okay. So, right. Definition. In general, if P hat of T is the position of an object, at time T, then the following. P hat prime of T equals V of T is velocity. Not just in the linear case, right? In general, we can differentiate P hat, that gives us the velocity, V hat. This is speed. And we had double prime of T, B hat prime of T to A hat of T is acceleration. Okay, that's points 1 and 2 or 3, probably somewhat familiar. This is exactly the analog of what you learn first, probably in calculus, when you do physical motivating examples about position, velocity, and acceleration. What is this quantity? Remember, we're overloading throughout this course the double bars. Yeah. Yeah, it's the magnitude of the velocity vector at time t. Right? Remember, this is a vector quantity, so double bars means magnitude, not absolute value. That's what they're for scalars. Okay. So, right, this is just, again, just like in calculus 1, when you have a position function, you differentiate to find velocity. If you take the absolute value of the velocity function, you get the speed. Now, in the context of vectors, we take the magnitude instead of the absolute value. I mean, really, you should think of absolute value as the magnitude of a vector in R1, right? Doesn't matter if it's pointing this way or that way. You're just looking for the length of the thing. So we just choose the positive side because we want length to be positive, right? Magnitude is just defined to be length, right? We just have to use a different formula for it because we have more dimensions. Okay. All right. So let us record some nice properties that the derivative of a vector value function possesses. Okay, let's first take scalars A and B in R, and we'll take F hat, G hat. Differentiable single variable functions into our n, and let's let m of t be a differentiable real value function. Then say a bunch of things. Just notice here, no hat on the M, right? So its output is a single real number. Yep. Okay. Given a fixed constant vector, W hat W1, W2 through Wn. The derivative of W hat is just the zero vector, right? Just as in single variable calculus, when we take every real number viewed as a function, right? It's just a constant function. Likewise, we can here take a constant vector viewed as a vector valued function, which has constant output, just the vector. The derivative of such a function is zero. The zero vector, to be precise. Okay, 2. A times f hat plus d times g hat prime equal to A times f hat prime plus b times g hat prime. Is known as the linearity of the derivative. This is a form of the chain rule. F hat and goes with M T, which is equal to F hat of M T. This isn't the statement, right? This is just, we familiar with this definition? The open circle, the composition of functions. This means I take T, I make M operate on T, and then I make F operate on M of T. Exactly whatever is here. Okay. Which is sensible, right? Because M of T is a real value function. So I put some arbitrary real number T into M, I get a real number out. That output can be the input of F hat. Yeah. Okay. So that if we wanted to take the derivative of this composition of functions, F hat prime of M of T. Oh, sorry. F hat of M of T prime. Prime goes on the outside to start. I'm taking the derivative of this whole function. This is equal to M prime of T times F hat prime of M of T. Okay, so we remember what the chain rule says from calculus 1, right? If I want to take the derivative of g of f of x, I take the derivative of the outside, g prime of f of x, times the derivative of the inside function, times f prime of x, right? The exact same thing is going on here, right? I take the derivative of the outside, f hat prime of m of t, times the derivative of m of t. Why did I put the derivative of m of t up front though? So it doesn't matter, right? Scalar multiplication is commutative, it can go on either side. But it's kind of conventional to write scalars to the left of vectors, right? So this emphasizes that m prime of t is a scalar function. So it's on the left, right? Scaling this vector value function. F prime, f hat prime. Okay. This is all notational stuff that might seem somewhat foreign or hard to keep track of, but just take a little bit of practice to get used to it. Okay. Okay. Right. So now, here's another way that we can use the function m, right? So remember that m is a scalar value function. So I can since m is a scalar value function, I can also scale f hat by the function m, right? I can just take t and evaluate m at t and f hat at t and scale f hat of t by m of t. That's what this notation is. Okay? That's what this function means. Okay, suppose I want to take the derivative of this function. What do? Well, this is a scalar product. How do I take the derivative of a product? Yeah. Yeah, the product rule. Right. We'll just apply the product rule here. Okay. So this is the same as m of t times f hat prime of t plus m prime of t times f hat of t. And again, just check that the dimensions of this operation are correct, right? We have a scalar function scaling a vector value function of dimension n. Have a scalar function and prime scaling a vector value function of dimension n. We're adding them together. And so we get a vector value function of dimension n. Okay. So right. Now, scalar multiplication is one of the types of multiplication that we talk about when we talk about vectors. And we're pleased to see that a version of the product rule holds in this scenario. Ideally, we would have a product rule for all the other types of multiplication that we've discussed about vectors, right? So, for example, what can I say if I want to take the derivative of the dot product of f and g? Well, again, the naive generalization of the product rule holds here. Okay. So that is to say, it's f hat prime of t dot g hat of t plus f hat of t dot g hat prime. Okay, so the product rule holds for dot products as well. Okay, and then likewise, you can say just the same thing for the cross product. When we take the derivative, right, we get f hat of t cross g hat prime of t plus f hat prime of t cross g hat of t. What did I forget to say here? There's one critical assumption I have to make in order to state the product rule for the cross product. What is that? Yeah.
Not the zero vector.
No, actually, this still holds when one of them is the constant zero function. That's fine, or one of the derivatives is zero. They're in R3, yeah. When n equals 3. When n equals 3. Very important there. That's the only time the cross product is defined. So 6 holds only when Rn is R3. That is to say, the output of f hat and g hat are both 3-dimensional vectors. Okay. Good. Okay. So. This one. Okay, let's do an example. Let's say that a hat going from R to R3 is differentiable. So that a hat evaluated at 1 is equal to the vector -2, comma 0, comma 1. And a hat prime evaluated at 1 is equal to 5, 5, 5. Okay. Furthermore, let's let b hat of t be given by the formula t squared t cubed t to the 4th. Let me ask you to calculate the derivative of a hat of t cross, oh, sorry, actually, our standard notation for this is a hat cross b hat prime of t. I just put of t all together up front. Oh, and also, you don't have enough information to calculate that for t. Evaluate this derivative at 1. What I meant to say. Sorry. Okay. So how do we proceed? Well, first thing to notice is that we know that A goes into R3, and just by the way that B is written, it also goes into R3. So this is well defined. At least we know we can actually apply the product rule for the cross product, right? So what information do we need to calculate the derivative of the cross product of these functions? Yeah.
You have one, and you have five.
Yeah, exactly. Good. So b hat evaluated at 1 is 1 squared, 1 cubed, 1 to the 4th, i.e. 1, 1, 1. Then let's calculate B hat prime of T. What's the derivative of B hat? Yeah, so what is that? Very good. Or T cubed. Excellent. Okay, now we can evaluate B hat prime at 1. We get 2, 3, 4. Okay. Now we can just apply the product rule for the cross product, right? That is to say, A hat cross B hat prime evaluated at 1 is just A hat evaluated at 1 cross B hat prime evaluated at 1 plus A hat prime evaluated at 1 cross B hat evaluated at 1. Okay. Well, we know the specific vectors for all 4 of these quantities. Right? So what is A hat of 1? Okay. -2, 0, 1 cross. We just calculated B hat prime of 1 is 2, 3, 4 plus A hat prime of 1 is 5, 5, 5 cross B hat of 1 we calculated to be 1, 1, 1. Okay, so somebody tell me how to calculate this cross product. We'll use the definition, yeah, we'll calculate some determinants, but maybe we can save ourselves a little work by analyzing the situation on a broad scale for a moment. We're definitely going to have to take this determinant. We're going to have to compute this cross product from the definition. Is there any time-saving maneuver we can make here? Yeah. These are parallel, right? One is a scalar multiple of the other. What do we know about the cross product of parallel vectors? It must be the 0 vector. This becomes the 0 vector. So now we only have to calculate a single cross product, right? Which, you know, calculating cross products is a pain in the neck. So that's good. All right. So let's just do it then. Determinant of ij. Okay. -2, 0, 1, 2, 3, 4. Right. So we get -3 I hat plus 10 j hat minus 6 k hat. Or as I personally would idiosyncratically write, parenthesis notation. That's what we were given in the sense of the problem. But again, it doesn't matter if you want to leave it in IJK. Okay, good. So remember, it's very often to your great benefit to take stock of what computations you actually need to make before you just start applying formulas left and right. Yeah. Taking this observation, cut our calculation time in half. Right? Okay. Good. Okay, so let's do some more examples. Okay, so let's suppose an object moves along a circle. of radius r. Centered at 0, 0 in R2, i.e. the origin. In a way, so that its position, p hat of t, is differentiable. Let us show the position vector is always orthogonal to the velocity vector. We had t. Okay, so how do we start? What do we know about position based on the setup of the problem? Well, what do you mean by starts at the order? Not exactly. We're supposing our object moves along a circle, and the circle is centered at the order. So actually, our object never touches the order.
PFT no hat is always gonna be the same.
What is P of t with
So
no?
just the scalar quantity of the distance from the center.
The magnitude
Magnitude.
of P of t. Yeah, good. It's always a constant. What constant in particular? R, exactly. Our object is constrained to be moving on a circle. So when we take the absolute value, I'm sorry, the magnitude of its position, that will always be R. Okay, here's the schematic diagram. Okay, here's my best approximation of the circle. We have radius R. Here's our object. This is its position at time t. R. So this means that as we're moving around this circle, the magnitude of our position will always be R. So know that the magnitude d of t is always equal to R. Okay, so there's a bit of a leap that we have to take here. Notice that what we're trying to do is prove something about the orthogonality of two vectors. How do we evaluate whether two vectors are orthogonal or not? Yeah.
Then if you take this dot product and it's 0.
Right, when the dot product is 0, we know that our vectors are orthogonal. In fact, that's an if and only if statement, right? Two vectors are orthogonal if and only if their dot product is 0. Okay, so with that broadly in mind, how can we start to deal with dot products based on this information that we have deduced? What's a formula that relates the dot product to the magnitude of a vector? Yeah. What do you mean by that? So that would be a scalar, right? Because the dot product is a scalar and the magnitude is a scalar. So yeah, you're really close to the thing I'm driving at here. If you dot a vector, yeah, exactly, right. So this is the relationship between the magnitude and the dot product, right? So in other words, if I square this, if I square both sides of this, I can get some expression involving a dot product, right? So this implies that r squared is equal to the magnitude of p hat of t squared, which is equal to dot product of p of t itself. Now, where do we go from here? Okay, maybe let me give you a hint of where we might be able to go. What's the relationship between position and velocity? The derivative, I think I heard someone say, right? Velocity is the derivative of position. So I should differentiate something. What exactly? Yeah.
New equation and then plug it back in.
Yeah, so let's differentiate both sides on the far ends of this and see what we get. Okay, so so what's the derivative of r squared with respect to t? Zero, yeah. R is just a constant, right? R is just the radius of the circle. So its derivative is zero. So r squared prime 0 is equal to the derivative of e dot p. So here we'll use the product rule for the dot product, right? This gives us p hat of t dot p hat of t. I guess I should write this on the next line. Myself in a space. Right. P hat of t dot p hat of t plus the derivative of t, that is to say p hat of t dot p of t. The dot product is commutative, right? So this just gives me 2 times the dot product of p of t and p of t. So I have 0 is equal to 2 times this dot product. Or in other words, p hat of t dot v hat of t is equal to 0. Yeah, which is just what we wanted to show. That the position is always orthogonal to the velocity if our object moves in a circular path in a differentiable manner. Okay. So this is kind of took a couple insights, right? But I hope that the steps that we took together kind of illustrate how you might puzzle this out, right? It's like, okay, here's the information I'm given. How do I try to combine all this information to resemble some formula that I know, right? Okay. Good. Okay, great. So everything I've said so far about Yeah, sorry,
Sorry if I missed this, but the reason the derivative of R squared is zero is just because R squared is a constant.
that's right. Yep. Good. So everything we said so far about the properties of vector value functions have been pretty straightforward generalizations of the stuff we knew from calculus 1, right? Now we're going to get into some of the important properties that we will study that kind of you saw in calculus 1 in a disguised form, but now we're going to be more explicit and precise about them. Okay. So, ish. Let's take P, any function from R to Rn, and we'll call it regular. At a point T naught, if and only if P hat prime of T naught exists and is not the zero vector. In such a case, we call T naught a regular point of T hat. Okay, this is fairly innocuous, right? I'm just saying that we're differentiable and non-zero. Okay. But it turns out that this extra condition of being non-zero is of vital importance to us. It's what allows us to give meaning to the analog of what a tangent line is for a curve, right? Calculus 1 is all about the interpretation of the tangent line in some capacity, right? Kind of like the main thing that we talk about at the beginning of calculus, right? So in order to give this concept of tangency a coherent generalization to n dimensions, it really relies on this idea of regularity. Okay, I'm going to say a lot more about this. I'm just giving you a vague overview before we dive in. Okay. So here's the theorem. Again, we'll take P to be a vector value function of a single variable. And we'll assume that it's continuously differentiable. In an open neighborhood of T naught in its domain. And we'll also assume that P hat is regular at T naught. Then what we can say, there is an epsilon greater than 0 such that the image of P hat restricted to T naught minus epsilon comma T naught plus epsilon is a smooth curve. Which we'll call C. And the vector P hat prime evaluated at T naught is tangent to C at P hat evaluated at T naught. Okay, there's a lot to unpack here. All right. So yes,
What does it mean to be regular?
what it means to be regular is to be differentiable and the derivative is not the 0 vector. Yep, that's our last definition. Okay. So there's a lot to unpack in this statement of this theorem, right? First of all, what's an open neighborhood? Yeah. Okay, so yeah, remember we're in R here. The R is the domain of P hat, right? So here's R. And here's this point where P hat is regular, T naught. An open neighborhood around T naught is just an open interval, right? A, B. So we write T naught is an element of the open interval A, B. Open neighborhood. Okay, we say open neighborhood because we're going to use the same terminology when we start talking about regions around a point in Rn. But for now, when our domain is just R, an open neighborhood is just an open interval. Open neighborhood equals open interval in just R1. Yeah.
Is that like bar notation after the P, the last line of bar, but ended?
This is restricted to, is what this means. So yeah, we'll get to that just now as well. Actually, we're almost out of time. Right, so we know what continuous differential is. We now know what an open neighborhood is of T naught. We know what regular means. Right, so yeah, let's just finish by saying what this bar means. Okay, so P hat first of all, this subscript here is a smaller open neighborhood around P naught, right? I'm letting epsilon be perhaps very small, so that I get some smaller open neighborhood inside my original open neighborhood. Okay, and when I write this vertical bar, this means P hat restricted to this interval. So if p hat is defined on all of R, I'm considering a new function here, which has domain just this tiny neighborhood here. Okay, it does exactly the same thing as p hat. It's just defined on fewer values. Yes. Epsilon is any positive number, but we think of it as getting quite small. Okay, great. So we'll pick up talking about this theorem on Wednesday. And good luck on the quiz. You guys are going to do great.